all. Hope I am audible. Okay. So yesterday we started our VHDL history. Okay, how the evolution of the HDL has been bent. So today we will try to understand the design of top-down and bottom-up design. Okay, approaches. What are the approaches that is we are using? Okay, so those things we will try to understand. So designing the model digital system such as processor, controllers, SOC and communication hardware requires a systematic methodology. Okay, it requires some systematic methodology. So the two fundamental approach used in VLSI designs are, okay, so they are using the two fundamental designs. So top down design approach and bottom up design approach. So these methodologies help manage design complexity, improve modularity and accelerate the development. Okay, so these are something where they were. 1 second guys. Okay, so these are some methodologies help manage design complexity, improve modularity and accelerate the development. So why this design methodologies matters? Okay, as the chip complexity increases, okay, when the complexity of the chip is getting increased, the transistor count grows dramatically and multiple design team work in parallel. Multiple design teams, they will work in parallel because there is a growth in the complexity and the transistor count grows. Okay, and we want to verification efforts also increases, and since they are multiple design teams are working, they want to integrate, that becomes a challenge. Okay, and timing closure becomes a critical. So without a structured approach, there will be a design error increase, debugging become difficult, reuse become poor and project schedules slip. So these are some points which we want to take care. So in the top down design approach, the definition what they are telling is, it starts from the highest level system specification. We will tell the specification what the system want to do, and progressively we will be moving, we will be splitting into the smaller modules until the implementation level blocks are reached. Okay, so there is a system and this system divided into subsystems, and that subsystems is divided into molecules, block, logic and gates. You think of a human is one system, and humans made up of the organs, and organs made up of the flesh, and the flesh made up of, so something from the top we are moving into the cellular thing, that you can give make as an example for the top down approach. Now the focus is system behavior first, how the system is going to behavior first, and that architecture is going to be the first, then comes the implementation. So first the design and all the things, then the implementation is going to be later. So this is the design flow of a top down approach. So we will specify architecture definition is happening, then we will go and do the subsystem partitioning, then module design, then for that we will go for RTL implementation, then gate level design, then the physical implementation. So from the specification we will go to the physical implementation, This is where the top down approach. So our system specification, everything will be the top requirement, and from there we will go for architectural definitions and all subsystems modules, and then comes the physical implementation. This is where the top down design approach. So for example, if we want to design a UART controller design, okay, we will start with complete requirement. What is the requirement? It want to transmit, it want to receive, it want to generate the baud, control logic and status registers. These all are the requirement. Okay, then we will go for a breakdown. So this is the whole UART module. So we will try to further subdivide TX module, RX module, baud rate generator, register interface, and some finite state machine we controlling the these modules. It is the further breakdown, and I mean the breakdown, first breakdown. In the further breakdown, we will go and break down the TX module, RX module for baud rate generator, register interface, and all those things. We will go and do the further shift registers, finite state machine for that, bit counter. So these implement follows after the architecture definition. So first we will go and define the architecture, then slowly we will break down it. So from the top, slowly we are break down it, and we will go and implement the hardware in the things. So from start is from the abstract specification, decomposition based, and architecture driven, and modular development and scalable approach. So these are something which is considered in the top down design approach. So when we speak about the advantages, when we try to speak about the advantages in the top down design approach, okay, better system planning, architecture is clearly defined before coding. Before we start the coding, we define what it want to be and how its functionalities and everything has been defined clearly. For example, what is the width of the data path, and what are the interfaces we are going to use, and how the protocol is going to behave. Those all are clearly defined. This is an example, but if you need more things, you can go and define the stuffs. Okay. And because of this, the management, large design, we can easily manageable. Okay. So for example, the processor can split into fetch code, decode code, execute, memory, and write back. So such kind of things we can, first the processor want to do these things, then we can split it into the stuff. So we can easily manage the steps. And then parallel development, different team can work independently. They can work independently of the work. Okay. So one team can work on RX, one team can work on TX, one team can work on verification. So from the top down design approach, these all are the advantages, and easier verification planning and better reuse planning. It can be done in a strategic way. Okay. So these are something which we have to understand. The main disadvantages is, okay, we need a in-depth knowledge about the system, how it going to work, and the architectural knowledge. Okay, because everything is going to depend upon the specification. So if the specification, from the specification, we are going and down and implementing the actual physical stuff. Okay, that is the idea. Now, if the initial thing itself, if it is low, okay, if the initial thing itself low, okay, someone is asking the link for today's class, you can send it in the group. If anyone, you can send it in the group, so they will get the link. Someone is asking, okay, so you guys send the link. Okay. So the disadvantages is it requires strong architectural knowledge. Okay, it requires a strong architectural knowledge. Okay, thank you guys. And then longer initial planning, that means more time we have to spend before implementation, because the specification makes everything. If anything wrong in the specification, then the total will be wrong. Okay, and risk of over engineering. Okay, so because sometimes our human mind, it will think in an over way and we will give the over specifications. It will create unnecessary complex in the architectures. So we have to be careful. So mainly the experience thing. Okay, so that we will be able to work with it. Okay, today we have a lot of lab practicals we have to do. Okay, with the AND gate only we are going to work, and we are going to work top down approach and bottom up approach with the AND gate. With AND gate itself we are going to understand this concept. Okay, so please be prepared for that. Okay, now comes the bottom up design. Okay, so maybe within now next 10 to by 10 minutes the theory part will be getting over, then fully it is going to be practical soon. So the bottom up design, it is a definition. What the definition they are telling? No, from the small building block, from the gate level they will make it. Okay, from the cell level they come to the human level. It is something like, okay, the top to bound, it is something like this. Here it is going from here to here. So start from small basic building blocks, combines them into larger modules, and finally construct the full system. And finally we are going to construct the full system. So glades we have, blocks we have, modules, subsystem, then system. The reverse will become our top down approach. This is becoming to the bottom to up approach. So where we will implement first, then the composition based on the growth. Okay, so that is what the thing. So but the latest thing, everything is going with the top down design. Okay, so from logic gates they will go to small functional block, from that reusable modules they will go for subsystem integration, then the complete system integration they will go on do it. This is the one the other way of design. For example, they will start with adder, multiplier, register, ALU, comparator, and multiplexer. Okay, and they will combine this data bath. So they will add combined CPU core, then complete the processor. So they will implement this first, then by combining all the data paths, and they will add the control logic, and they will combine the CPU core to complete one processor system. See, previously the processor system they will go and specify it, then the architectural define will come and they will break down into small things. From there they will go on. Here they are starting it from the smaller stuff and they started combining it, and then with the help of this they add the control logic and they will combine into the core and they will go on do the things. Okay, so that is specific driven, this is implementation driven, and component assembly module centric and incremental design. Okay, these are something which you guys want to understand. So the advantage is, okay, we can go and reuse the adder, multiplier, registers, and then comparators, multiplexers. We can go and reuse it. That is what these things. Okay, so even if we have created the UART, you can reuse this UART IP, intellectual property, SPI, FIO, I mean FIFO, ALU. Okay, So it is faster for known designs. If building familiar systems, faster development is possible. And the testing is also a small modules we can easily verify independently. Okay, and it is good for library based design, standard cell and IP heavy flow benefits. So these all are some benefits when we go into the bottom up design approach. Okay, the main disadvantage is it is poor global optimization. We cannot optimize the whole system something, and locally optimized blocks may create poor overall architecture because we are building it from the small blocks. When we try to optimize the small blocks, it will give the poor overall architecture. Because of optimization we are done it in the locally. So these all are some disadvantages. So the area efficient modules causing timing bottlenecks. Okay, so from the smaller modules you have to create a bigger module, and if we need the area efficient, it might be a bottleneck. And the main thing is integration. Small thing, when you try to easily we can split, but when it comes to the unity, no, always it is a problem. So modules may not integrate cleanly. That is what the things. Okay, so interface mismatch, timing mismatch, reset mismatch, and difficult system planning. So architecture emerges late. So these all are some issues where we will be facing when it goes to the bottom up. Okay, so I have captured system specification is the starting point, basic block is the starting point. So first the architecture level, then here the first is implementation level. So the abstraction is high, and from that they will go into a low thing. Okay, abstraction is high, and then okay. Next, planning, strong early planning, minimal early planning, reuse. It is already planned, and bottom up is it natural. Naturally, we have to reuse it. For this, we have to plan and use it. Integration is easier when it comes to the top down, but it is harder. Structure, it is incremental. Scalability is excellent and limit for very large systems. Okay. So when you try to talk the top down, they start with the behavior. What behavior we will tell? Red light want to go for 30 seconds, green light want to go for 20 seconds, yellow light for 5 seconds. So we will define a finite state mission, timer and output, then we will implement the RTL. Bottom up approach, directly we'll go for counter, timer, comparator, flip-flops, then they combine into a controller and then they will do it. So stop up is the requirement specification, everything they will take and go and do the things. Here they will go with the things and then they will combine and then they will go. Okay, so that is the difference between the top down and the bottom up approach. Okay, so in the application specific integrated circuit, mostly they will go for top down. The reason is very large complexity, timing closure, architecture planning, power budgeting, verification planning. Okay, these all are top down. So like SOCs, CPU, AI accelerators, those are all ASIC designs. So they will go for this top down. For FPGA, they will go for mixed. Top for one module, top down, and then the rest they will go for and down up. And for the small projects, you can go for bottom up is possible. Okay. But for the large FPGAs, they will go for the top down. Okay. So what is the relation with the top, these with the hierarchical design relations? Okay. So top down naturally supports hierarchy because we specify SOC, then we will try to split into memory, UART, SPI and DMA. So each block further decomposed. So naturally it is an hierarchical design relation. Okay. Now hybrid approach where the industry reality. Modern designs often combine both top down for definite SOC and bottom up for reuse verified intellectual property blocks. So this is the most practical approach. They will use both top down and bottom up. Okay. So designing the processor, architecture planning, they will go and use. And for ALU, FIFO and IP reuse, they will go for the bottom up. Okay. So top down verification planned from architecture stage, bottom up verification mainly module first. So modern best practices verification is integrated throughout throughput. Okay, throughout the things they are going to verify it. Okay, so in the top down mistake, what they will do, no, when the architecture weak and they will ignore the implementation constraint, because there will be some constraint during the implementation, they will be ignoring it, and unrealistic interfaces. These all are top down mistakes. Bottom up mistakes means the mainly depending on the integration planning, incompatible modules, duplicate functionality, and timing closure problem. These all are the common design mistakes which we'll do it in the things. Okay, so the recommended is top down architectural definition, modular hierarchy, bottom up for IP reuse, and earlier verification planning and synchronous design methodology is the recommended best practice what they are trying to give us. Okay, screen is visible, screen is visible. Okay, I can sure, maybe you can log it on log on, maybe I can try one more thing. Okay, hope now screen is visible. So real industry example is designing a UART, top down, define protocol behavior and block partition. If you want to go for bottom up, reuse the FIFO baud counter shift registers. Hybrid means faster and reliable design. Okay, so these are some theory. So in summary, we went and looked into top down approach, bottom up approach. In industry reality, top down for planning, bottom up for implementation and reuse. That is what is happening. So they are going and using both the things in reality. Okay, so these all are summary about our top down and then the bottom up approach. Okay, now from, okay, I hope you guys got some idea about the theory part of the things what we have been till now looked into it, top down and then bottom up approach. You can think as a human as a system. When we split organs and then inside the organs molecules, compounds, a lot of things, and then we go into the atom, that is top down. Okay, from the cell, if you move to our whole system, that is the bottom up. Okay, so these are the things which you have to understand it. Okay, screen is visible, Ramya. Okay, Jammu Ramya, screen is visible. Maybe you have to log out and log in. Okay, so now we will come to our practical part. Okay, we will look into our practical part. We will come to our practical part. Okay, now let me take the project. Opa. Okay, now let me take the training CSC info VLSI practicals. Okay, let me bring that to you. Okay, yesterday we went and used, okay, yesterday we went and used 1 second. In one single file, okay, in one single file we went and created and we are able to do the things. Okay, so let me create a file. Okay, one underscore and gate. Okay, so let me put everything inside it. Okay, now let me create a second one. Okay, a better. Okay, first we will start it with better. Okay, so inside this, let me open the terminal. Okay, so I think, okay, screen is visible and you guys are able to get the things. Okay, so now we will try to have a better ungate dot v. So here I am going to have an approach. Yesterday I wrote the ungate, and even to test also I have went and given those things in the same file. Now let us separate it. Let us try to separate. Okay, we will have our design file a separate, and the thing which we want to verify, we have to test that design. Design is nothing but our hardware. Okay, designing is nothing but our hardware. So that design we will keep it separate, and then we will try to go and add the things. I mean the verification things. We will try to keep it in a separate thing. Okay. So for that, okay, let me draw the same AND gate with the. I'm not going to change the gate and all. I am trying to give. I'm trying to give a better code when we come to the yesterday part. Okay, so now we are going to define a hardware here itself. Okay, so let us use a module. Okay, once we have given the module, we want to go for end module. This is the universal law. Okay, we have to keep that in the mind. Okay, so now my module name I'm going to keep as the AND gate only, so that we can go and define it. Okay, so when you are trying to have the design, you have to give this module in something like this. Okay, so here we are going to give what is our input. Okay, I'm going to input. It is of wire type. I will teach this wire and all later, but for a time being, you guys be try to get an idea. That's it. Okay, you think there is a two input. We have a two input. Okay, you have a two input. Then what is the output? Output, that is also an wire we are giving it, and output let it be y. And then let me finish that module. I am finishing that module. So now I actually created a gate which is having two input and one output, and actually I didn't tell anything what is the relationship between the input and output. So now I am going to give the relationship between the input and the output. Okay, so now this tells that, okay, you are using that and the input output, those things you are trying to assign, you are trying to create an AND gate. Okay, so this tells that, okay, oh, you guys are trying to create a AND gate. So my design got over. If you want to check my design is very good, very later. Okay, hyphen lint hyphen only, and then let me use AND gate. Now yesterday it was giving me a lot of error, but today it went and given me, and it is not giving me, it is not shouting me. Okay, now the thing is, I want to test my hardware, that is the design file. So I want to write a test cases. Okay, they will call it as test bench. Okay, So let me create a test bench. So for the test bench, usually we will start with the letter TB. Okay. So test bench for my undgate dot v. Okay. So there is a test bench for my, anyone, what is the tools that SAR is using? iVerilog, that is in the first class I went and used iVerilog, very later Yogsys, all are open source tools. Okay. So, and I am using Ubuntu system, open source. Okay, I am a fan of open source. So Vim, okay, so I am trying to, this Vim is an text editor. Whichever editor you want, you can go and use it. Okay, so now I want to introduce a time. Okay, I want to introduce a time. Okay, so for that, escape has been written, insert more. Okay, let me take this. Okay, TIMESCALE, time scale 1 nanosecond. We are considering 1 nanosecond bar 1 picosecond. Okay, and then we want to test the module. So for everything we have to write the module keyword. That is the thing. Okay, so now the module is going to be undgate. Okay, our module which we are going to test is an undgate. We are telling it, wherever you write module, you have to go and end the module, otherwise, okay, it will be the thing. Okay, so now for testing, we want to store the input. How are we going to store the input? These are the things we are going to use it. Okay, and then reg b, and then wire y. Okay, so because since it's an output, we are going and giving it wire. This reg wire, those things I will teach you later. Okay, those things, still we have more than 15 days left. Okay, I will come to the module and everything. There is a separate session for those things. But before that, you guys try to understand my, see, right now from the yesterday's close code, I am trying to give you a refined code. I am trying to give you a refined code. Okay, compared to yesterday, compared to the yesterday. That is what. Okay, so now I created a test bench and I created a value which I want to store. Okay, but the thing is, what I am going to test. So I want to test the AND gate. Okay, and I will tell that device under test, DUT or UUT. I think DUT will work. If DUT didn't work, then I will go for UUT. Okay, and then this is the port and this is the signal I am going to give. I am telling that. Okay, and then this is the input port B. Okay, and this is the signal which I have been kept B. Okay, I am linking, now only linking. I am creating the instance for our hardware and I am trying to link the port and the signal. That is the thing which you have to understand. Okay, then I am making it. So this AND gate, I am creating and test an instance over that. Okay, I am trying to create an instance. Now I want to test the inputs. So for that, I want to use initial and begin keyword. Okay, I want to initial and begin keyword. Once we begin, we want to end it. Once we begin, we want to end it. So let me go and write whatever the things we want to test. Let me go and write it over here. Okay, since I need mp dump file, since I need, okay, I need a file to verify the graphics, I mean the graphics tool. I want to convert that into an VCD file so that VVP tool will go and convert it to me. Okay, and then this is the thing which the variable I want to go and pass for it. Okay, dump variables wheres. Okay, so I'm going to pass, okay, something like, let it be, always we will try to give the 0, and then which thing I want to pass, test bench and get as the variable to that. Okay, and then when I was, and I want to see the things in the clearly in the, when I in the console also. So what I'm going to do is I'm going to get the timing information. Okay, let me, the timing information may be percentage 0t. Okay, and then, and I want to see when the input is this much, when we have input I want to look into binary, not in decimal. Okay, what is the input, and then what is the output, and then I mean input, two inputs, no, two inputs, sorry, two inputs, and then the output also in the binary I want to go and look into it, and I want to see the time. This parameter will get me the time. A will get me the input. B will get me the the input, and Y will get me the things. Okay. Now I am going to use the test cases. So I have the test cases when the input is 0. Okay. When the input is 0, and again when both the inputs are 0, then I'm going to give the time, let it go for 10 nanosecond, let it go for a 10 nanosecond. Okay, then I'm going to test another combination when b is equal to 1, what is its value, and I'm giving an a 10 nanosecond of gap. Okay, and then I'm going to give the test case for all the test cases, a equal to 1, and then b equal to 0. Okay, and I'm going to use it for the 10 nanoseconds. Okay, I'm going to use for 10 nanoseconds. Then a equal to 1, I'm giving all the verification methodologies to this. Okay, what all things my hardware I want to undergo, I'm giving all the possibilities of input, and what is the output I want to go and check it over there. Okay, so I went and given it. Now I think I made one syntax method for the timing thing. No, I think I missed it. Okay, next let me finish it here. I'm giving these things, it you will be understanding this in a later classes, but for a time being, believe me. Okay, for a time being, believe me, I wrote a test cases. I have wrote the test cases. Okay, I have wrote the test cases. So let me check. Okay, let me try to use iVerilog, iVerilog, and gate and test bench, and let me get an output of sim.out. I hope it worked well. So it went and given me this one. So by using the VVP tool and the sim out, okay, it is telling that unable to open the input file because I didn't properly. Okay, sim out. So now I got an, somewhere I made a mistake in this, I think so, that we will check it later. Okay, so during the this second, okay, 10,000 something during second, whatever it might be, when a is 0, okay, something I I went and messed up with the uh, binary. Okay, so let me go and check with the TB stuff. Okay, let me go and use the TB. ABY, okay, percentage B, percentage 0T. Okay, instead of percentage, what I have given, B equal to percent B. Oh, okay. I went and give. Okay. Thank you. Monitor I have to change. This one. Correcta? Okay. A, B and Y. I hope it works now. I think so. Okay. I very lag. Then let me try VVP. Okay, now it is working. Okay. So now we are getting the for A0, B0, Y equal to 0. For A0, B0, Y equal to 1. A1, B0, Y equal to 0. These are the things I am able to get it. Okay. Now, once I run that, I got a file called dump.vcd. So using that GTK wave and then dump.vcd, I am able to see a graphical interfaces. Okay, where I can see the waveform. If I click this, if I click this, if I click this, if I click this, okay, I am able to look into it. Okay, let me come to the 40 nanoseconds. So now you can see what is the value of here. You can see that that value is getting changed. So now somehow I got a code which is having an, what I will tell, a design file and then a, what I will tell, an test bench where I can go and do the things. So I made it separate, hardware design separate, testing separate, and I'm able to get the things. Okay, so this is the better code compared to the yesterday stuff. Okay, now I'm going to show you the two different things, bottom up and bottom down approach. Already I have the code. I don't want to spend time in typing this code. Okay, so somehow I given you idea on typing these things. Okay, now let me go and open the code which I already have. Okay, which I already kept it in the bottom up and the top down approach. Okay, so let me open that. Okay, okay, I have a bottom and the top down. Okay, so first we will go for a bottom. Okay, this is the 4-bit now AND gate. Okay, so this AND gate we went and created. Okay, so now we are going to look for an a bottom up approach. What you are going to do, sir? Yes, I want to create a 4-bit AND gate. Right now we are using only 1-bit AND gate. Right now we are using only 1-bit AND gate where it can do AND operation between the only one bits, one and the other thing. Now I want a 4-bit AND gate. So I am starting it with the 1-bit. This is the already the gate which I went and designed it. Okay, this is the 4-bit AND gate. I mean 1-bit AND gate. Now I am going to design a 4-bit. Okay, I am going to design a 4-bit. So for the 4-bit, I need an input of 4-bit. That is where we went and used it. And the input also want to be 4-bit. And the output also we need the 4 bits. So we went and created a 4-bit. Okay. Now we want to assign. Directly if we give, it will not work. We are going to use this gate to make this gate. How we are using that name and gate. Okay, we are using that, and we are creating a gate 0 only for the first bit. Okay, so this is the port, this is the port, this is the port, and we are giving the signal only the first signal. Okay, likewise we are creating a second instance of giving only the second signal, and the third instance of giving only the third signal, and fourth instance of giving the fourth signal. Okay, so we have created a and gate of 4 bit with the help of a 1 bit and gate. Okay, so this is where from the bottom we are slowly moving into the top down, I mean slowly moving up. So bottom up approach. And the test bench, if I want to open the test bench, okay, if I want to open the test bench, you can clearly see that the same thing I have given, nothing, the same thing. I created the module and end module, that's wrong. And then what is the signal I am going to give? These are the signals I am going to give. And what is the device under test? DUT. Okay, so in that, this is the port and this is the signal I am giving it. This is the signal I am giving it. Then the same thing, initial, begin and end. And I am trying to, since if you need you can keep it, otherwise don't need, but you somehow you have to verify the signals for this and all used. Okay, and I am using the same, I am trying to give the binary. Okay, previously I went and given only one set, so I don't want to mention anything, but here I want to mention the size, and then what is the format. B is for binary and 4 bit 4, so that is the 4. Okay, this is the syntax they are following, so no other go, you have to follow the same syntax. So I was trying to give only small combinations. If you want all 16 combinations, you go and give the 16 combinations and you can go and test. It is up to you. Okay, so for creating a test bench, you have to start with module, you have to end with module, then you have to create an instance, and then instance for that hardware, and you begin and then go and finish it. Okay, so this is a small thing regarding the bottom up approach. Now let me open the terminal. Okay, let me open the terminal. In that, let me destroy this terminal and let me go and use this. Okay, so now I verilog, I have AND gate. Okay, AND gate 4 bit, and again I have AND gate and underscore gate. Then I want to test it with the test bench, and let me put it in the sim.out. If you want the output file, however you want, you can go and give it. So for me, the sim.out got created. Now let me do VVP, whether I am getting an dump file. You see, it is giving all the verification. I'm not here to go and verify these things. Okay, you can go, it will be correct. And if you see that I am getting a dump file, VCD, and 4-bit VCD, and 4-bit VCD. I didn't give dump.vcd. Okay, if you see that, if you try to see this file, okay, here I given the dump as and 4-bit.vcd. Whatever the file name you give, accordingly it goes and dump it. Okay, so now I use GTK wave to show the flow of the diagram. Okay, and 4-bit VCD. Okay, so now you can see that. Okay, you can open that, and if you double click it, you can see each bit by bit, and if you scroll, if you go to 40 nanoseconds, okay, you will get the things, the inputs and everything will be changed, and you can go and verify it. Okay, so this is what the bottom up approach. By using the bottom-up approach, we went and looked into it. Then we will go for the top. We will go for the top. Okay, so in the top, we directly went and created. Please try to understand. Directly we went and created and 4-bit, and we went and assigned the things. This is the specification. We are not using the lower module. We went for the specification and then we directly went and created the things. Okay. So here we have a 4-bit input output and directly we are assigning it. We are not reusing the AND gate. We are not reusing this AND gate. What we are directly doing is we are directly moving with this approach. Okay, we are directly going and moving it with this approach. Now the test bench is same. For this also the test bench is going to be same only. Okay, the same test bench only, with that we are going to test, because it's for the AND gate, the same. And this is the device under test, and then dump for same dump file, and I'm going to use the same variables. Okay, so maybe I can put here 10, maybe I can change that. Okay, if you want anything to add, you can add. However, the things you want to add, you change the combinations and you go and work on it. Okay, so it's up to us. Okay, you can have this, you can have 16 combination, this you can have 16 combination, I mean 16 things, and however you want you can change it. It goes something in a permutation. If you put permutation combination, it goes a lot. Okay, so now let me open the terminal and let me go and tell you how to compile the things. It is so easy. iVerilog. Here I have and for topdown.v. That is the only file we have to go on, do the things, and we have test bench also. So we have to use test bench and -o sim.out. Okay, simulation.out only I put sim. Whatever file name you give, no problem. Okay, when I try to use this VVP, I am able to generate a dump file. Through the dump file, I can go and see the waves, or else in the console you can see the output with the help of monitor. With the help of monitor, we can go and see the output. So GTK wave, I'm able to see the GTK wave, and then the VCD file, this has been created, and let me put it over here, and then let me enter it, and then you can see that you can see the same thing. You will be getting the same output. Okay, if you click what are the inputs it's have and all the things, you can see the output also. And if you click this is the thing, this. Okay, so you can, okay, these things you can go and visit and you can see it. Okay, so hope you guys got an idea of how from the yesterday's thing, somehow we went and modified. I didn't teach till what is module and all those things. I am making you guys to familiar with the code, first thing. Okay, I am trying to make you familiar with the code, the first thing. Okay, so slowly we will try to understand it, and at one class I will try to give you a big picture, so you will be getting a more clarity. Okay, so hope you guys able to understand. If you have any doubt, please let me know. Before that, they will ask, anyhow they will ask me about the PPT. I will give the PPT. The code you can get it from the online itself. That is not a big deal. So if you guys have any doubt, please put it in the chat. EDA playground use Chayandi sir for easy understanding. Use Chayandi sir. I already told, only for the few classes I will go and use EDA playground. but rest I told I will go for only uh, I will go for only the Linux platform. In the first class itself, I told if you want to use, you can use EDA playground, no problem. But I want you guys to understand about the open source and all those things. That is what uh, my intention. Okay, that is where my intention. Okay. Okay. Thank you. Okay, I hope you guys don't have any things. Okay, see, parallelly, if you want, you can work with EDA playground. Okay, but I will go with only the Linux system, Ubuntu systems, and all those things. I mentioned it clearly in the first class itself. Only for you guys, make you happy. I went a few times for EDA playground and try to work on it. Okay, there is no, this code will work in the EDA playground also. No problem for you guys. Okay. Is there any possible using mobile this tool? No. In the mobile, I don't think we don't have such kind of things. Maybe you can go and install the uh, Ubuntu, and in that, if you need, you can go and use and install it. But that is too risky. It's depend on you. Okay. Okay, guys. See you tomorrow. I mean, see you on Monday. Thank you. Happy weekend. Okay. Bye. See you all.